Okay. അപ്പോൾ നമ്മൾ എഴുതിയത് രണ്ട് പാർട്ടിക്കിൾ. Okay. So PA plus PB is equal to PC. The method പഠിക്കാൻ വേണ്ടിയിട്ടാണ് ചെയ്യുന്നത് മെയിൻ ആയിട്ട്. രണ്ട് സൈഡിലും square on both sides. Okay, these are 4 momentum. PC square is equal to PA plus PB square. Okay. Now നമുക്ക് capital M നൽകാം. We took it as capital M. M square is equal to, all right, this is M square C square.
M square C square.
Yes. Do PA square plus PB square plus 2PA dot PB. This is for scalar product of 4 momentum. Okay. So this is equal to M square C square plus M square C square, because these are identical particles, right? And here 2, we write the components EA by C, PA vector, right, multiplied by this is EB by C, comma PB vector, right? So this is equal to, you can write this as 2M square C square plus this is 2EAEB divided by C square, right? It multiplies the 0th component, the time component, minus PA vector dot PB, 2PA dot PB. All right. This minus comes because we are in Minkowski space. All right. Now this is equal to 0 because one of the particles is at rest. Right. So this becomes 2M square C square plus 2. And what about the energy? The particle of mass m whose total energy is twice its rest energy. This is twice the rest energy, twice rest energy. So that is 2 MC square, right? And EB is simply MC square because it's at rest. This is the rest energy divided by C square. Okay. Now, if you just solve this, you'll get this is M square C square. And now if you just solve for M or M square, so this is equal to, I think one of this we can cancel, 2M square C square plus, oh, wait a second. So there's a 2 here, right? There's a 2 here. Okay, this 2 we have to carry over here, right? This 2 has to be there, right? Okay, so that's equal to 6 M square C square, or M is equal to square root of 6. All right, it's the same answer we got when we did it using the previous method. But in many cases, this method is much easier, okay, much quicker, right? So we just need some practice. Okay. Now they can ask what's the momentum? What's the momentum? All right, they can also ask for the momentum, free momentum. Okay, momentum of particle C, right? What's the momentum of particle C? Okay. Now the easiest way to do that, we know that we can just use momentum conservation, right? Because we know that one of the particles was at rest. Okay, we have got PA plus, right, or A plus B gives C. So one of the particles was at rest. Okay, this is at rest, for example. So the momentum of C will be the total momentum of A and B. Right? We'll just write that this is 3 momentum. So PC vector is equal to PA vector plus PB vector, but PB vector is 0. So it's simply PA vector. Right? We know this. This is the 3 momentum. Okay, this is just momentum conservation. So PC vector is equal to PA vector. Now we can find PA vector because we have the information that EA is equal to twice its rest energy, right? 2 MC square. Is that correct? That's given. Okay. Now you can find, okay, one way to do this is we know that E is equal to gamma mc square. You can find gamma and then you can find velocity and find gamma mv square, but that's quite tedious, all right? It takes a long time, all right? For example, you can find, say that gamma is equal to 2. So 1 by square root of 1 minus v square by c square is equal to 2. Okay, now you square and solve for v, you get v, and then you find gamma mv. That's one possibility. There's an easier method because we know this relation, right? E square is equal to p square c square plus m square c raised to 4. All right, you can always use this. This is much quicker. Okay, so this means that p square or pa square c square is equal to e square minus m square c raised to 4. Okay, or pa square is equal to e square by c square minus m square c square. Okay, we can do this. Right now, this we know because e is given by 2 mc square. Right, e is given by, let's say pa here, ea, right? So this is 3 momentum, right? 3 momentum. So now we just use this relation. Okay. ea is 2 mc square. So if you square it, it becomes 4 m square. There's okay, for m square c raised to 4 divided by c square minus m square c square. So that's equal to 3 m square c square. All right. So this is modulus of pa square. So from here you immediately get pa is equal to, or the momentum, the magnitude of the momentum, okay, is root 3 mc. Okay, that's also really quick. Okay, so always remember this relation. Right? This is very useful, especially if the energy is given. You can find momentum using this in a very quick manner. All right. Not only that, you can also find the velocity now. Okay, sometimes they also ask for the velocity. Right? Now, how do we find the velocity? We say that we know that p is equal to gamma mv. Okay. All right. Let me take the magnitude. All right. This is magnitude. So this is all right. Now E is equal to gamma mc square. So you see that P by E. All right. P by E is equal to, you can cancel this gamma. All right. That is V by C square. So in order to find V, you just multiply C square P divided by E. All right, this is the relation for velocity. Okay, now we can easily find the velocity because we see that V is equal to C square multiplied by P by E. What was P? That is square root of 3 mc. And what was E? E was, we found okay, this is the momentum of the initial particle, right? And so by momentum conservation, this is also the momentum of the third particle, right? So we have got the result Pc is also square root of 3 mc. Okay, so that's why I have a square root of 3 mc here. And what was the energy? What was the energy? If they strike together, what's the mass of the resulting composite particle? We only found the mass, right? So I think this may be a bit. What's the? Just a moment, let me just check how to find the velocity. We found the momentum, but we didn't find the energy. Did we find the energy?
ഇല്ല എനർജി നമ്മള് കിട്ടിയില്ല. ആദ്യത്തെ നമ്മള് മാസ് എടുത്തു,
മാസ് മാത്രം കണ്ടുപിടിച്ചുള്ളൂ അല്ലേ?
മാസം മൊമെന്റ്.
All right, so wait, let me see how to do this now. We've got അങ്ങനെയാണ് ഇത് m is equal to square root of 6 uh, Okay, now ഇതിന്റെ velocity കണ്ടുപിടിക്കാൻ ചോദിച്ചില്ല, ഞാൻ just extra തന്നതാണ്. പക്ഷെ ഇത് കണ്ടുപിടിക്കാം. All right, there are different ways you can do this. One way to do is that you know the mass and the momentum. All right, you can find the energy like this. E is equal to p square c square plus m square c raised to 4. Am I right? So that would be 3 m square c square plus p square c square. All right. So just write E is equal to, I write EC is equal to PC square C square plus M square C raised to 4. Okay, that's equal to, so you square this, that becomes 3 M square C square multiplied by C square, so C raised to 4 plus, okay, what's the mass? That is square root of 6M, so that is 6 M square C raised to 4, so that becomes 3 plus 6 is 9, am I right? 9 M square C raised to 4, or the energy is equal to simply 3 mc square, right? 3 mc square. mc square. Now you can find the, right? Now you can simply divide it, so you see that V by C square, right? V by C square is equal to P by E. So it's equal to root 3 MC divided by 3 MC square. Okay. So that is, wait a minute. P by E.
ഇത് വി അല്ലേ കാണണ്ടേ സാർ? നമുക്ക് വി നിർത്തിയാൽ പോരെ അവിടെ? ഈക്വൽ ടു
Yes, you're right. V by C square is equal to root 3 MC divided by 3 MC square. Okay. So this is cancel. So you can, yeah, that's right. So V is equal to root 3, but C square. C square cancel. So it's root
C square more on C square root 3 MC.
1 by root 3 C. That's the answer. Okay. All right, that's correct. That's the velocity. അപ്പോൾ തന്നിരിക്കുന്ന റിലേഷൻസ് ഉപയോഗിച്ച് നമ്മൾ ഫൈനൽ ആൻസറിലേക്ക് എത്തുക എന്നുള്ളതാണ്. നമുക്ക് ആവശ്യമായിട്ടുള്ള റിലേഷൻസ് എല്ലാം ഉണ്ട്. ഒന്നുകിൽ ഫോർ മൊമെന്റം സ്ക്വയർ ഉപയോഗിക്കുക, അല്ലെങ്കിൽ എനർജി മൊമെന്റം കൺസർവേഷൻ ഉപയോഗിക്കുക. റൈറ്റ്, യൂസ് എനി ഓഫ് ദിസ് ടു ഗെറ്റ് ടു ദ ഫൈനൽ ആൻസർ. ഓക്കെ, ഇതുപോലുള്ള പ്രോബ്ലംസ് ചോദിക്കാറുണ്ട്. ഓക്കെ, നമുക്ക് വേറെ ഒന്നും നോക്കാം. Yes, so here is a question. Okay. A particle of mass m, okay, initially at rest decays into two pieces, okay, each of mass m, right? So initial mass is m, right? It decays into two pieces, okay, each of mass m, right? So I'll write it like this. I'll say particle A goes to B plus C, right? Each of mass m. What's the speed of each piece as it flies off? Okay, speed of each piece. Fly off. Okay, so we've got I think we can just solve it using initially, because this particle is at rest initially. All right, initially the particle is at rest and decays into two pieces, each of mass small m. What's the speed of each piece as it flies off? Okay, there are different ways to solve this. To find the velocity. Okay, one way to do this. Okay, you can think of other ways. Okay, one way to do this is use the energy conservation, because the initial particle is at rest. Okay, in the laboratory frame, or in the frame that we are considering, the initial particle is at rest. So this is the initial energy. Okay, EA is equal to, we can write as gamma mc square plus gamma mc square. All right, this is the energy of A, this is the energy of B. All right, they both have the same mass as given by that. All right, we use the same gamma here. All right, that's the information that we take from the question. Why do we use the same gamma here? Because of momentum conservation. All right, because of momentum conservation. Because momentum conservation says that PA plus PB is equal to 0 because initial momentum is 0. Right? So if you take the magnitude, or you can say that PA is equal to minus PB, okay, or simply modulus of PA is equal to modulus of PB. Okay, there's no modulus here, I'm sorry, minus PB vector. Okay, so this means that gamma M, since this momentum is gamma MV, all right, this momentum also has to be gamma MV. So they have both the same gamma factor, right? We can use this here. So you see that MC square is equal to 2 gamma MC square. Okay, now we can just solve for gamma from here. Okay, so you see that gamma.
ഈ റെസ്റ്റിലിരിക്കുന്ന ഒരു കേസിലും നമുക്ക് ഗാമ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്യേണ്ട കാര്യമുണ്ടോ സാർ? ഇല്ലല്ലോ.
എവിടെയാ റെസ്റ്റ്?
അല്ല, ഞാൻ ഇവിടെ അല്ലേ ഞാൻ അപ്പൊ ആദ്യത്തെ അത് ഇപ്പൊ നമ്മുടെ MC സ്ക്വയറിനില്ല, ഗാമ MC സ്ക്വയറിന് പകരം MC സ്ക്വയറിന്, അതായത് ഏത് പാർട്ടിക്കിളും റെസ്റ്റ് എന്ന് പറഞ്ഞു കഴിഞ്ഞാൽ
ഗാമ 1 ആണല്ലോ.
ഗാമ 1 കൊടുത്താൽ മതി.
അതെ അതെ, അതായത് റെസ്റ്റ് എനർജി ഇതെപ്പോഴും ഓർക്കാവുന്ന കാര്യം. റെസ്റ്റ് എനർജി നമ്മൾ ഈ ഫേമസ് ആയിട്ട് എപ്പോഴും പഠിക്കാനുള്ള എനർജി MC സ്ക്വയർ റിലേഷൻ ഉണ്ടല്ലോ, ഇത് ആക്ച്വലി റെസ്റ്റ് എനർജിയാണ്. ഓക്കെ, ടോട്ടൽ എനർജി കിട്ടണമെങ്കിൽ ഗാമ MC സ്ക്വയർ ചെയ്യണം. So if the particle is at rest, it has energy MC square. If it's not at rest, if it's moving, it has an energy gamma MC square. Okay. Okay.
Okay.
Okay. ഇവിടെ നമുക്ക് ഗാമ കണക്കാക്കാം. ഗാമ is equal to m by 2n. അല്ലേ? Right. ഇനി ഇത് രണ്ട് സൈഡിലും സ്ക്വയർ ചെയ്തിട്ട് വിക്ക് സോൾവ് ചെയ്താൽ മതി. കാരണം ഗാമ നമുക്കറിയാം 1 by square root of 1 minus v square by c square ആണ്. Alright, that's equal to m by 2m. So just square on both sides. Okay, and you can solve for v. You'll get v is equal to c multiplied by square root of 1 minus 2m by m square. Okay, that's the answer. ഇത് വേറെ രീതിയിലും ചെയ്യുന്നതിനെ കുറിച്ച് ആലോചിക്കാവുന്നതാണ്. ഫോർ മൊമെന്റ് ഉപയോഗിച്ചോ ഇങ്ങനെയെങ്കിലും ഒക്കെ. ഇത് ഏറ്റവും സിമ്പിൾ ആയിട്ടുള്ള മെത്തേഡായിട്ട് തോന്നും. ഓക്കെ, ഓൾറൈറ്റ്. So that's the velocity. Okay, now here is a very important problem. Right, this is a standard problem. Okay, this can be asked somewhere. So here we consider the reaction. Okay, the next problem. A high energy proton strikes a proton at rest. Okay, that is and the reaction is given like this: P plus P, right? A high energy proton striking a proton at rest, okay, gives P plus P plus P plus P bar. Okay, that's 3 protons and an antiproton. Okay, 3 protons and an antiproton. What's the threshold energy for this reaction? What's the threshold energy for this reaction? What's the threshold energy for this reaction? Okay, so this means the minimum energy of the incident photon. Okay, by threshold energy means what's the minimum energy of the incident photon? Minimum energy of incident photon. Okay, now this threshold energy thing, it's very difficult to formulate in the laboratory frame, all right, because one particle is moving. We don't know anything about this momentum. All right, so we go to a frame called the center of mass frame. We go to a frame called the center of mass frame. All right, so in center of mass frame, what do you mean by center of mass? You are going to a frame which is in the center of mass, which is the center of mass of these 2 protons. Okay, which is the center of mass of these 2 protons, which means that the center of mass is at rest. In the frame that we are considering, the center of mass is at rest. So if you look at it from the center of mass frame, right, you will see that you go to this frame and the corresponding reaction goes like this. All right, if it is the laboratory frame, there's a proton coming and hitting a proton at rest. In the center of mass frame, you'll see that both protons, because they have the same mass, they are coming in opposite directions with equal speed. All right, so center of mass frame, the total momentum is 0. In this frame, in center of mass frame, okay, the total momentum 3 vector is equal to 0. I'll write it like this. Okay. So since this is equal to 0, all right, in the center of mass frame, in the center of mass frame, the right hand side also the total momentum has to be equal to 0. Okay. So we get a nice information here. If you go to the center of mass frame, the total momentum on left side is 0. That means the total momentum on right side also has to be 0. Okay. All right. So now what do you mean by threshold energy of a reaction? Okay. Threshold energy of a reaction means there is no kinetic energy. All right. There is no kinetic energy for the, so if you go to a laboratory frame, the threshold energy means that if you hit these protons exactly at this threshold energy, all these protons would be at rest. Okay. There is no kinetic energy for them. All right. That's the meaning of threshold energy. So by threshold energy, we mean energy, there is no kinetic energy. Kinetic energy is equal to 0. Okay. All right. So these are the information that we are going to use. So how do we solve this problem? How do we solve this problem? Okay. So we have to use the fact that the 4 momentum square, all right, or P dot P, we can write like this: P mu is relativistically invariant. It's relativistically invariant. Okay, this is the idea that we are going to use, which means that you can calculate this from any frame you like, you will get the same number, right? You calculate this P mu from whether it's in the center of mass frame or in the laboratory frame, you will get the same result, all right? So this invariance is a nice information, all right? We can use this information that gives you an equation, and that equation will be sufficient to solve here. Okay, so what we do this, how we do this is, okay, I think I'll write it here. Okay. Okay. So we'll first do the problem. The easiest way to do this, all right? We can say that, let's write the 4 momentum. Let's write the total 4 momentum. Total 4 momentum before collision. Before collision in the laboratory frame. Okay, laboratory frame. Okay, and we'll write the total 4 momentum after collision in the center of mass frame. Center of mass frame. Right, you will see the convenience here. Okay. All right. Now let's first, in the laboratory frame, we can say that before collision, okay, the total 4 momentum, I'll write it like this: P mu total is equal to E plus mc square. All right, this is the energy of the incident proton, this is the energy of the proton at rest. Okay, divided by c, that's the 0th component, and then you also have modulus of p vector. All right, so we can take the direction of movement of photon as the x direction. All right, we'll take this as the x direction. So y component and z component are 0. Okay, now we can write the total 4 momentum after collision in the center of mass frame. All right, so we have written the total 4 momentum before collision in the laboratory frame. Now we write the total 4 momentum after collision in the center of mass frame. All right, so we'll write P mu prime total is equal to. Okay. So what's the total 4 momentum after collision? Okay, what's the total 4 momentum after collision? Okay, in the center of mass frame. In the center of mass frame. Right. So how do we write this? Okay, so in the center of mass frame, as I said, in the center of mass frame, okay, we said that initial momentum is 0. So total momentum, this is the important point, total momentum of all particles. This is 3 momentum, okay? Total 3 momentum of all particles is equal to 0. All right. So we'll have the energy here that's equal to, because there are 3 protons and 1, we have got legs, right? P plus P gives P plus P plus P plus P bar. All right. So total energy, okay, we say that all these particles are at rest. All right. All these particles are at rest. So total energy, what's the total energy now? It is the energy of this proton plus this proton, this proton, this proton. All right. Now we are saying that we are calculating the threshold energy, right? We are calculating the threshold energy. Okay. So threshold energy is just the sufficient energy to create these particles. Okay, create these particles, which means these particles will be at rest. Okay, there is just enough energy to create these particles and they will be at rest. If there is extra energy, it will be converted into kinetic energy. All right. So in order to find the threshold energy means that all these particles are at rest. Particles are at rest. Okay, so that means the total energy becomes simply 4 mc square. Okay, mc square for this, mc square for this, mc square for this, and mc square for that. Okay, totally 4 mc square. So the zeroth component is divided by c. Okay, and we take each individual momentum to be 0. Each of the individual momentum is 0 because we are calculating the threshold energy. Okay, we didn't do anything much. We wrote the total energy before collision. We wrote the total energy before collision in the laboratory frame, and we wrote the total energy after collision in the center of mass frame. All right, and in center of mass frame, we said that not only the total momentum is 0, but each of the individual momenta are 0. All right, now it's clear that p mu is not equal to p mu prime because they are in different frames. Okay, these are in different frames. All right, so the individual components are not equal, but we know that p mu, okay, there's a total here, there's a total here, p mu total is equal to p mu prime total, because, okay, this is the important thing. All right, because this quantity is invariant, it does not change when you change the frames. Is this clear? Is it clear or not?
Yes, sir.
Okay. E relation, just square and you take the scalar product and then solve. All right, you'll get the energy. All right. So if you take this this thing, you see that the square on left hand side, it is because the total energy was E by C plus MC square. All right. I'll just write it again here so that, okay, I'll write it here itself. I'll just write it here, okay? Now you take the scalar product, all right, of the 4 momentum square on both sides and make use of the fact that this is invariant, all right? Make use of the fact that this is invariant. ചിലപ്പോൾ ചോദിക്കാൻ സാധ്യതയുള്ള ചോദ്യമാണ്. ഞാൻ പഴയ നെറ്റ് ക്വസ്റ്റ്യൻസ് എടുത്ത് നോക്കുമ്പോൾ ഇങ്ങനത്തെ ചോദ്യങ്ങൾ ചോദിക്കുന്നുണ്ട്. ഈ ചോദ്യം സ്പെസിഫിക്കലി ചോദിച്ചിട്ടില്ല, പക്ഷേ ഈ കൊളീഷന്റെ പ്രോബ്ലംസ് ചോദിക്കുന്നുണ്ട്. ഞാൻ എക്സാമ്പിൾസ് കാണിച്ചു തരാം. ഓക്കെ, സോ all right, this is the thing. Okay, so we do this, we make use of this fact p mu total. Okay, I've already written it here. You take the scalar product on both sides. All right, the scalar product on left side is simply E plus mc square divided by c square minus modulus p vector square. Okay, because it has a modulus p vector square. This is equal to what is on the right hand side? It is 4 mc the whole square. Correct? Yes. Okay. Now we can make use of this relation because we know that p vector, modulus of p vector is equal to, or p vector c square, or p square c square is equal to e square, because we need to find the energy, right? It's e square minus m square c raised to 4. So is that correct? Yes. Right? P square c square equal to e square minus m square c raised to 4. So we can write this as e by c plus mc whole square minus modulus of p vector square. We'll write it as e square by c square. So that would be, there's a minus here, so I'll put it outside, e square by c square plus m square c square. All right, because you are dividing by this c square on both sides. Okay. Okay. So this is equal to 4mc square, right? Now it's just a matter of solving this because we have got the e here. We have got the e here. All right. So if you square this and subtract, you will see that we can just square this. We can solve for e. I'll do it here. Okay. This is e square by c square plus m square c square plus 2e by c mc, right? Minus e square by c square minus m square c square is equal to 16 m square c square. Okay. So is that correct? This e square by c square and e square by c square are gone. So you see that m square by c square gone. Am I making any mistakes? No, I think I made a mistake somewhere. Is there a mistake somewhere? Square by c square plus m square c square is 2e by c mc. Okay, sorry, it's a minus here. It's a minus here. Okay. It's a minus here. So here it becomes a plus. All right, now it's fine. So you see that this is 16 minus 2. So you see that 2m square c square plus 2em is equal to 16m square c square. So 2em is equal to 16 minus 2 is 14, right? M square c square. Okay. So you see that this m and this m gets cancelled. So you see that 2e is equal to, yes, that's correct, 14 mc square, or E is equal to 7 mc square. Okay, E is equal to 7 mc square. This is the threshold energy. This is the threshold energy. This is the threshold energy. Okay. All right. So this is an important question. All right. This is a place where we made use of the fact that this the square of the 4 vector is a relativistically invariant quantity. Okay, this is I think the simplest way to do this. Otherwise, it gets really complicated. Okay, now we can also find the threshold kinetic energy. Right, we can also find the threshold kinetic energy. Okay, the question can be asked also in terms of threshold. This is the threshold energy. Okay, threshold kinetic energy. Right, so threshold kinetic energy, you can find it by you know that kinetic energy is equal to E minus mc square. All right, E threshold energy is 7 mc square. So the kinetic energy is equal to, the threshold kinetic energy is equal to 7 mc square minus mc, that is 6 mc square. Right, that's the threshold kinetic energy. All right, so the incident proton should at least have 6 mc square of kinetic energy. Okay, only then this reaction can take place. All right, so the incident photon must carry at least 6 times its rest energy for this process to occur. All right, okay. All right, so is it time? Can we do one more problem? I think we'll do one more problem. Okay. This is a problem that was asked for net JRF June 2011. Right? Consider the decay process tau minus equal to gives pi minus plus nu tau in the rest frame of the tau minus. Right? The masses of tau minus, pi minus, and v tau are m tau, m pi, and 0 respectively. All right. The energy of pi minus. What's the energy of pi minus? So what's the energy of pi minus? Now, how do we do this? Okay. So we'll immediately write the forward momentum. Okay. P tau is equal to P pi plus P nu. Okay. We did a problem of this kind, I think, already. All right. But this question was asked for net, so we'll solve also this. Okay. Now, the easiest way to do this, what's the energy of pi minus? We just write P tau is equal to P pi plus P nu. Okay, but this P pi, it's a bit problematic. All right, what's the energy of pi minus? We only need the energy of pi minus. All right, so this P pi vector we don't know. We don't know this P pi vector. Okay, but we know that P tau vector is equal to 0. P tau vector is equal to 0. All right, and we also know that P nu square is equal to 0 because it is massless. Okay, so in order to eliminate this P tau vector, right, we'll combine it in this form. P tau minus P pi is equal to P nu. Okay, now you square on both sides. You see that P tau square plus P pi square minus 2 P tau P pi is equal to 0 because P nu square is 0. Okay, P tau square is m tau square c square and P pi square is m pi square c square minus 2. What's P tau? P tau is, we can write it as E tau divided by C, okay, comma P vector, P tau vector multiplied by, you have got P pi as E pi divided by C, comma P pi vector. Is that correct? Right. Now this is equal to, the rest I'll write here. So this is equal to, you see that this is m tau, we can put the c square, m tau square plus m pi square, okay, is equal to, okay, I'll write it like this, minus 2, now you take the scalar product, all right, e tau e pi divided by c square, correct, okay, minus p vector tau dot P pi vector. Okay, there's a minus here, so this will become plus. Okay, there's a minus outside. Okay, now what is this P tau dot P pi? It's equal to 0. Why? Because it said that initially this P tau is equal to 0. It's at rest. So this term goes. We have eliminated this P pi. Okay, now from here you see that. And E tau, what's E tau? Since it's at rest, since it's initially at rest, we know that E tau is equal to m tau c square. Now you just use this. You see that c square m tau square plus m pi square. You can take this to the other side. That's equal to 2 m tau c square divided by, so there's also e pi here, e pi divided by c square. Okay, now we solve for e pi. E pi is equal to m tau square plus m pi square, okay, divided by m tau square plus m pi square divided by, there's also c square there, divided by 2m tau. Okay, 2m tau. Yeah, this is the answer. All right, so this problem was asked for net JRF exam in June 2011. This is the easiest way to do it. You can also do it using energy conservation and momentum conservation separately. Okay, all right. Now you can also find the momentum if you want. Okay, you can do it as an exercise. What is P pi vector? What's this momentum? All right. In this case, we eliminated this P pi vector, all right, because we combined it with P tau. All right. So in this case, we will have to eliminate something with P nu and start with P tau minus P nu is equal to P pi. You can do this. All right. No, that's also not very useful. Yeah, I think you can do this, and then you will get the answer. Okay, you also may have to calculate the momentum Yeah, you have to calculate the momentum in this way. You also will have to calculate the velocity sometimes. All right, so you can do it in the usual manner. Okay. Here is one problem. Recently, this also asked for NET exam, June 2014. Okay, so such problems are asked. The recently discovered Higgs boson at the LHC experiment has a decay mode into photon and a Z boson. Photon and a Z boson. If the rest mass of the Higgs and Z boson are 125 GeV by c square and 90 GeV by c square respectively, and the decaying Higgs particle is at rest, the energy of the photon will approximately be, what's the energy of the photon, right? What's the energy of the photon? Okay, can we do that? We need to find the energy of the photon. Let's see how to do this. All right, so let's first write. We have got a Higgs boson which is decaying into a photon and a Z boson. A photon and a Z boson. I'm not writing the charges here. All right, this is zero charges. Okay. The decaying Higgs particle is at rest. The energy of the photon, we need to find the energy of the photon. So if you look here, we can write the four momentum conservation as Ph is equal to P gamma plus Pz. Okay, Ph is equal to P gamma plus Pz. Okay, and we don't know the momentum of the Z boson, but the mass is given. All right, the mass is given. Okay, so we need to eliminate the momentum of the Z boson. So we'll write Ph minus P gamma, these are four momenta, is equal to Pz. Okay. Now, if you square this on both sides, you simply get mz square c square. All right. So you don't have to worry about Pz vector. You don't have to worry about this. Okay. This information is not needed because that information is hidden in the fact that when you square this, you'll get mz square c square. Okay. Now you square this. So Ph minus P gamma square is equal to Pz square, that's equal to mz square c square. Okay, so this is Ph square minus P gamma square minus 2Ph P gamma is equal to mz square c square. Okay, so this is Ph square is mh square c square. P gamma square is 0 because it's photon. All right, so minus 2. We've got Ph P gamma. What's Ph? It's mc square because initially the Higgs boson is at rest. So that's mhc square divided by c, comma 0 because it's at rest initially. All right, so Ph vector is 0 multiplied by P gamma, that is E gamma divided by c, comma P gamma vector. We don't know that. All right, we don't know that. But now when you combine them, you'll see that this term will cancel off this term. Right. So when you combine those, you see that mh square c square minus 2 mh square c square, mhc square divided by c multiplied by E gamma by c, that's equal to 0. Okay, now it's just a matter of solving for E gamma. Not 0, I'm sorry, it's equal to mz square c square. It's equal to mz square c square. All right, now it's just a matter of solving this equation for E gamma. So you see that so 2mh E gamma is equal to mh square c square minus mz square c square, or E gamma is equal to mh square minus mz square c square divided by 2mh. All right. Now we have got the expression. We know mh, it's given. Now we just solve it. You know mh, it's given. You know mz, you know mh. You just substitute all in there, right? So mh square minus mz square. What's mh square? That is 125 square. Okay. You are multiplying this by c square, right? So this c square will go. Right, so this is mass is given in units of energy. So 125 GeV will be mc square. Okay, that's the idea. 125 GeV is mh c square. So instead of mh c square, Wait a second, it's mh square c square here. It's mh square. Is it mh square? Correct. All right. So it's easier to write it like this. You can write this as mhc whole square minus mz c whole square. Okay. So you will have to pull the c square outside because I've multiplied by c square inside. So this c square will vanish. Is that correct? Yeah. You can, sorry, mhc square, c square, mz c square, c square. So you'll have to pull out a c raised to 4 here. All right. So that will become, am I correct? Yes.
Yes.
Right. So I'll have to pull out a c raised to 4 here, right? 1 by c raised to 4. Okay. So that's 1 by c raised to 4 will come here and it will become 1 by c square. So in the on the denominator we'll have 2 mh c square. Is that correct? Fine. മനസ്സിലായോ?
Yes, sir.
അപ്പൊ നമുക്ക് ഈ 125 GB per c square എന്ന് പറഞ്ഞാൽ അതിന്റെ അർത്ഥം m c square എന്ന് പറയുന്നത് 125 ആണ്. So instead of m c square here, I can write 125 square because there's a square here. There's a square there. And mz c square, that is what's z minus 90 square. Okay, because mz c square whole square we have got here. Okay. And divided by twice mhc square. Twice mhc square is again 2 into 125. Okay. This is E gamma. Now this is easy to do, I think. You can either do it numerically, but net exam no calculator no we can. So I think easy thing to do is we can write this as 125 plus 90 multiplied by 125 minus 90. Is that correct? So that would be 125 plus 90 and then 125 plus 90. 125 to 215, right? 215 multiplied by 125 minus 19. 35 or no? Yes, 35, correct? 215 into 35 divided by 250. Okay, so if you solve that, what answer do you get? This is 125 plus 90 multiplied by 125 minus 90, correct?
ശരിയാണ്.
Okay. അപ്പോൾ ഇത് ഇനി സോൾവ് ചെയ്താൽ സോൾവ് ചെയ്യുമ്പോൾ ഇത് 5 കൊണ്ട് ഹരിക്കും. ഇവിടെ 7, ഇതിനെ 5 കൊണ്ട് ഹരിച്ച് എത്ര വരും? 50 അല്ലേ? റൈറ്റ്. ഇനി ഇതും സോൾവ് ചെയ്യാലോ. എങ്ങനെ ചെയ്യാം? Again, I think you can divide it by 5. We'll get a 10 here. And what do you get here? 215 divided by 5 എന്താണ്? 41 ആണോ? No, 43 അല്ലേ? It's 43. So you have got 4.3 multiplied by 7. What is it? 4.3 multiplied by 7. Simple numerical calculation check ചെയ്യണം കേട്ടോ. ഞാൻ just ചെയ്ത് നോക്കണം. Okay. So you multiply by 4.3 by 7. What is it? 30.1. Okay. So 30.1 GeV is the energy of the photon. Okay. So you see that there is this answer 30. So we'll choose the most suitable answer. Okay. That is 30 GeV. Is that fine? Okay. Shall we do one more problem? Are you there? കേൾക്കാമോ?
കേൾക്കാം സാർ.
ഇത് മനസ്സിലായില്ലേ? കുഴപ്പമില്ലല്ലോ.
30.1.
Okay. Now, I think we can also do this problem. Right? This also relativity ingante ചോദ്യങ്ങൾ ചോദിക്കാറുണ്ട്. Okay, ഇതെല്ലാം ഞാൻ പഴയ ക്വസ്റ്റ്യൻ പേപ്പറിൽ നിന്ന് കളക്ട് ചെയ്ത പ്രോബ്ലംസ് ആണ്. Okay. The muon has mass.
നമുക്ക് ക്വസ്റ്റ്യൻ എഴുതി എടുക്കാൻ പറ്റുന്നില്ല. നമ്മൾ പ്രോബ്ലം വൈസ് മാത്രമേ ചെയ്യാൻ പറ്റില്ല. ഞാൻ സ്ക്രീൻഷോട്ട് എടുത്തിട്ടുണ്ട്.
ഞാൻ അത് നോട്ട്സിൽ ഇൻക്ലൂഡ് ചെയ്യാം.
അത് മതി.
നോട്ട്സിൽ ഇൻക്ലൂഡ് ചെയ്തിട്ട് അയച്ചു തരാം. ഓക്കെ. അല്ലെങ്കിൽ ഈ ക്വസ്റ്റ്യൻസ് അയച്ചു തരാം. എങ്ങനെ വേണമെങ്കിലും ചെയ്യാം. നോട്ട്സിൽ ഇൻക്ലൂഡ് ചെയ്യുന്നുണ്ടോ എന്തായാലും. ഓക്കെ, ഡോണ്ട് വറി. Okay, the muon has mass 105 MeV per c square and mean lifetime 2.2 microsecond in its rest frame. All right, so this is like the proper lifetime. Muon rest in the frame, the lifetime 2.2 microsecond. Micro na yes, micro. Okay, the mean distance traversed by a muon of energy 315 MeV. Okay, we need to find the mean distance. Okay, so the quickest way to do this, okay, there are different ways to do this, of course. One way is to see that it's given, mass is given, all right, mass is given, and the energy of the muon is given, energy is given, all right. So we know that E is equal to gamma mc square, all right. So 315 is the energy, that's equal to gamma multiplied by mc square is 105. Okay, mc square is 105. So you see that gamma is equal to 3, alle 105 multiplied by 3, alle, right? Yes, correct. So gamma is 3. You get gamma. All right. Is that enough? Now you know that the lifetime, the proper lifetime is 2.2 microseconds. All right. But what's the lifetime in the frame in which this muon is moving at this with this gamma? It will be, we know that delta t is equal to gamma delta t 0. Right. This is the proper time. This is the gamma factor. We already found the gamma factor. So this is equal to 6.6 microsecond, right? So the mean lifetime in this frame, okay, in the frame in which this muon is moving with this is 6.6 microsecond. Okay. Now the question is not the mean lifetime, but the mean distance traversed by a muon of energy. All right, we need to find the mean distance. For that, we need to find the velocity, because distance is equal to velocity multiplied by time. Okay, we need to find the velocity. What's the velocity at which this muon is moving? Now we can find velocity from gamma, right? Because inside gamma it's 1 by square root of 1 minus v square by c square. We can find the velocity using gamma. Okay, or we can find the velocity in a different way. Let me see. Okay, you can try. All right, this is easy. You just find 1 by 1 minus v square by c square is equal to 9, and from here we can find the velocity. Okay, and then you just multiply this v multiplied by delta t, and then you will get the answer. Okay, so you just solve this to find the velocity and do this. Okay, that's one way to do that. Okay, I want to try a different way here. Maybe this is easy, I don't know. Okay, you have to choose which one is easier for you. All right, so first we can find the momentum. Okay, momentum is equal to e square minus m square. Sorry, what's momentum? We know that e square is equal to p square c square plus m square c raised to 4. Okay, so p square c square is equal to e square minus m square c raised to 4. All right, or p square is equal to e square by c square minus m square c square. This is the momentum. Okay, so you can find the momentum as e square by c square. E square is given here, 315. Okay, that is 315 square divided by c square minus m square c square. All right, so that is mc whole. So it's mc square whole square divided by c square. Is that correct? M square c raised to 4 by c square. That will give m square c square. Correct. Okay. So that's equal to 315 square by c square minus mc square. Mc square is 105, so it's 105 square divided by c square. All right. Is this easier? Maybe, I don't know. All right, you can see which method is easier. Okay, maybe the other method gives you a quicker answer. Okay, so this can be found to be 315. Again, we can use this. This is 1 by c square 315 plus 105, 315 plus 105 multiplied by 315 minus 105. Is that correct? So it is 315 plus 105. Okay, that's 420. Is that correct? So 420 multiplied by 305 minus 105. It is 210. I think that's correct. I don't know. Okay. So you can check this. This is the momentum. Now we know that V is equal to C square multiplied by P by E. Okay. V is equal to C square multiplied by P divided by E. Okay. So that C square and this C square will cancel. So you will see that V is equal to 420 multiplied by 210 divided by what's E? E is 350. Okay. I don't know if this is easy. Okay. You have to check it. Is it easy to do this? Now you'll have to solve this, right? Is there an easy way to do this? 420, maybe it's all the same. Okay. All right, you can find the velocity from here. Now you just multiply it by 6.6 microseconds in order to get the mean distance. All right. So the distance will be 420 to 10 by 315 multiplied by 6.6 into 10 raised to minus 6. There's something wrong there, maybe, I think. Okay, you solve the numerical thing. Okay, that's how you do that. Okay, I'll explain again. From E is equal to gamma MC square, we found gamma to be 3. From there, immediately we found the lifetime, right, of the muon in this frame. From the proper lifetime, because proper lifetime is given, it's 6.6 μs. Now you need to find the velocity. I tried doing it like this. Maybe this is more complicated. I don't know. Okay. So 15. All right, or we can simply square this. Gamma square is equal to 9 and do that from there. You can find the velocity from there. All right, and you will see that the exact answer is not given. All right, you will see that it's something like 1.86 kilometer. Right, if you do this numerically, you will see that it's something like 1.86 kilometer, but the nearest answer is 1.98. Okay, you can check that. All right. Okay, we did a few problems. Okay, is there anything, any question? There is one more nice problem that we can do. Okay, there's one more nice problem that we'll do in the next class. Okay, which shows the simplicity of our method using 4 momentum. Okay, so shall we stop for today?
Yes, sir.
ഞാൻ പഴയ ക്വസ്റ്റ്യൻ പേപ്പർ നോക്കിയിട്ട് ഡോപ്ലർ എഫക്റ്റ് അങ്ങനെ ചോദ്യങ്ങളൊന്നും കാണുന്നില്ല. ഏതെങ്കിലും മുമ്പുള്ള ക്വസ്റ്റ്യൻ പേപ്പർ അങ്ങനെ എന്തെങ്കിലും ഉണ്ടോ? ശ്രദ്ധിച്ചിട്ടുണ്ടോ?